In this section, we'll be looking at antiderivatives, which are also known as infinite integration. And as you can kind of tell from the name, antiderivatives are the opposite of taking a derivative. So we're going from a function back to what the original function would have been before the derivative was taken. So for example, we have this function here, f of x equals 5x to the fourth power. So if we try to think of the function that has this derivative, it's not too difficult to see because it's a pretty simple one here. The original function here would have been f of x equals x to the fifth power. So if we take the derivative of x to the fifth power, we get 5x to the fourth power. Notice I use a capital F there to show it's not the same function. It's the function that came before the derivative. However, this is not our only option. In fact, we have many options for our capital F of x. In fact, we have infinite options, which is why this is also called infinite integration, because this function, f of x equals x to the fifth power plus 6, also has the derivative of 5x to the fourth power. I could use another function that looks like this, capital F of x equals x to the fifth minus 8. That also has the derivative of 5x to the fourth power. In fact, any constant that I add or subtract to the end of this x to the fifth here is still going to have a derivative of 5x to the fourth power. So the way that we will write this is capital F of x equals x to the fifth power plus capital C. And that capital C there is there to represent the constant in an integration problem. Whenever we integrate anything, we always want to put that plus C on the end of the equation, because when we take that derivative, that constant's going to go away. So any number could have been added to the end there. Just a little notation down here in the bottom, that capital F is used for the antiderivative, and we see right here that the derivative of capital F equals the f of x that you're trying to find the antiderivative of here. So that's a little bit of notation we'll see. Let's continue on with a little bit more notation. You'll recall that when we were doing derivatives, a lot of times our derivative would say dy dx equals we'll say dy dx equals some function. We'll call it f of x here. Now, in this case, we want to get back to an original function that's not the derivative, dy dx, but it's just the original function y equals. So if we wanted to solve this for the y here, first thing we would have to do is we'd have to multiply both sides by the dx. So that would give us dy equals f of x times dx. And then we would have to do something to get rid of that d there with the y. The operation that we are going to use to undo that derivative of y is called antidifferentiation or indefinite integration. So what we'll do here is we'll take this dy equals f of x dx, and we will integrate both sides. And this is my favorite symbol in all of calculus. I think it's so pretty. It kind of looks like a tall, skinny S. I didn't draw it so well there. But that's our integration symbol. So when we integrate a derivative, it just cancels out that. So we just have a y right here on the left-hand side. And when we integrate the lowercase f of x, we'll have this here on the other side, which the integral of that lowercase f of x is the capital F of x, and then we have to put a plus c here for our constant of integration. So a few things notation-wise. This part right here, this f of x, is called the integrand. So this part right here is the integrand. What happened there? And this dx right here, that is our variable of integration. Okay, so that tells us what we're integrating with respect to, much like it did whenever we were taking derivatives and we had to add in like a dy dx or something like that. So those are important parts. We call this c right here our constant of integration. And that capital F of x is our integral that we have. So these are all pieces of notation that we'll need for problems like this. So to move on, let's just do a few problems where we take the integral. So we're trying to think of what function has this derivative. So if we have little f of x equals 8, then the capital F of x would be 8x. And we want to make sure that we put a plus c here for our constant of integration, because that number could be added there on the end. So this would be our integral that we would have for number 1. For number 2, whenever we integrate f of x equals 0, we're looking for something that has a derivative of 0, and the only thing with a derivative of 0 is a constant. So this one actually is going to be capital F of x equals capital C, because there's just that constant is the number that would have that derivative there. For number 3, we've got 10x plus 3, so this one gets a little bit tougher, but still not too bad. What we've got to do here, if we have x to the first power right here, that means that before we took the derivative, it had to have been x to the second power. And so if we have x to the second power, we need to think what number times this second power here would give me the 10, and that, of course, would be a 5. 10 divided by 2 would give you that 5 that would be here. If we took that derivative, we would get 10x. For the 3, we would just have plus 3x, and then we must always put a plus c on the end there. For example 4, we get even a little bit more difficult. So our capital F of x here, our x to the third, we're going to have to increase that exponent by 1, and then we would need to think what number times that 4 would give me the 4 that's out front here is that coefficient. So that would just be a 1, which we don't have to write. Then we're going to have an x squared. We increase that exponent by 1 here because we have an x to the first power. And then what number times that 2 would give us 6, and that, of course, is 3. That's 3. Let's fix that. And we'll have a minus sign there. And then we'll have a plus 2x, and we can't forget to put our plus c there that I ran out of the room before. So there is our integral for example 4. For example 5, we are going to say capital F of x equals, we're going to have x to the 5th power, and here we're going to take that 40, divide it by that 5. That'll give us the number that we should multiply to get 40, so that'll be 8 here. Then we'll have minus, we'll have x to the 3rd power. 27 divided by 3 gives me 9. We'll have a plus 10x, and then we have to put a plus c there on the end for that. This last problem is a little bit trickier because we've got this number in the denominator. However, what we should probably do first here is say f of x equals, let's see, here. f of x equals negative 2x to the negative 3 plus 3. So we're going to follow the same pattern here that we were doing before, being careful with those negative exponents. So we would have x to the negative 2 power, because we're going to increase the exponent by 1. And then if we divide out front, negative 2 divided by negative 2, that would just give us a 1 here, which we really don't have to write. And then we'd have a plus 3x and a plus c. Now you might see this written back like this: 1 over x squared plus 3x plus c. Okay, so this brings us to some properties that we're going to look at. And in this chart here, I've got these properties, and they're sort of lined up with their differentiation and integration. So you'll notice over here that we are taking the derivative of a constant. Anytime we take the derivative of a constant, we get 0. So if we integrate 0, we're going to just get that constant back over here in this section. Next, if we have the derivative of k times x, we just get k. So if we integrate a number just like k here, which is some constant number, then we'll get k times x plus c. Finally, or not finally, there's a couple more here. So then if we have something where we're taking the derivative of one function plus another function, we can just take those derivatives separately, f prime of x plus or minus g prime of x. Same thing is true of integrals. If we are integrating f of x plus g of x, we can integrate f of x and g of x separately and just put that plus or minus sign in between them. The last thing that we have here is our power rule. When we take the derivative of x to any power, what we do is we subtract 1 from the exponent and we multiply out front by that number that we had. So like for example here, if I have x, if I have x to the 4th power, whenever I take the derivative of that, I just multiply out front by 4, which would be that n there. Then I'd have x to the 4 minus 1, which would be 3. So to integrate, our rule is the opposite of that. So to integrate, the first thing we would do is we would increase the exponent by 1, which we see right here. And then we would divide out front by whatever number that was, that n plus 1. So here, if we're going backwards, if we are integrating 4x to the 3rd with respect to x, then we would increase that exponent by 1, and then out front, that 4, we would have to divide it by this new exponent, which is 4. So that would just give us x to the 4th power. And then I should probably have added here that to this we have to put a plus c. So right here, we would also have a plus c for both of these. So that's generally your power rule for integration. Let's do just a few more. For example 7 and example 8 are just like the ones that we have already done. But for example 7 and example 8, the notation is slightly different. They give you dy dx equals 5x, and we know dy dx is another notation for the derivative, and they ask you to solve the differential equation. So this is a super simple differential equation. Differential equations have their whole entire classes whenever you go to college, and you can learn a whole lot of other stuff about it. But in the most basic terms, you have a differential equation here. So you could multiply both sides by dx here, and that gives you dy equals 5x dx. And then you would integrate both sides. You have to have that dx over there on the other side when you're solving this, because the integral of dy is y. You don't want the dx over there messing you up. And when you integrate 5x, you're going to increase your exponent 1. That'll give you an x squared. And then divide out front by that 2. So 5x over 2, or you could put 2.5 there if you would like. And then it's incorrect to say that the dx is replaced with a plus c, but you can kind of think of it that way, that dx is always replaced with a plus c, because anytime you integrate, you're going to have that plus c on the end. So this would be the solution to the differential equation. This is the equation that if you take its derivative gives you 5x. So it's really doing the same thing, it's just notation is a little bit different. So if we look at example 8, we would multiply both sides by dx, and then that would cancel our dx's over here, so we could integrate both sides. So on the left-hand side, we would just get a y. On the right-hand side, we would have x to the 4th. We'd do 8 divided by 4, which would give us 2. Plus, we'd have x to the 3rd. We would do 9 divided by 3, which would give us 3. And then we would have minus 4x plus c. Okay? Our last few are going to be well, this first one's not, but they're going to be a little bit trickier, not much. So for example 9, this is pretty straightforward. We're just going to have 3x minus, and then we'll have x squared, 5 divided by 2, so we'll just put 5 halves, plus, and then we'll have x to the 3rd power, and then we'll have 7 divided by 3, and then we'll put a plus c right here on the end. So this one is an integral here. We would just put an equal sign because this integral equals this expression. For example 10, before we integrate here, it is probably best for us to write this as x to the 1/2 power. So when we integrate that, we are going to add 1 to our exponent. So 1/2 plus 1 is just going to be 1/2 plus 2 over 2, which is 3/2, which most of you could probably do in your head. So, and should be able to do in your head. So our new exponent is 3/2. We have to divide the coefficient out front, which there is not 1, so that means there's like an invisible 1 right there. We have to divide that 1 by the 3/2. And this also you could probably do in your head, but if you can't, dividing fractions is easy as pie. Flip the second and multiply, so you would have 1 times 2/3, which would just be 2/3. So we are going to get 2/3 x to the 3/2 plus c. So if you have something that has sort of weird exponents, something with a root, change it to your fractional exponents first, and then just use your power rule. These last couple we're going to have to do that same thing with. So for 11, I would need to change this to the integral of x to the -4th power before I try to integrate. And now I can just use the power rule, and I will get x to the -3rd power. And then I need to divide the coefficient out front, which there's not 1, so it's a 1. I need to divide it by this new exponent, which is a -3. I must put a plus c on the end. You will probably see this written this way, -1 over 3x to the 3rd plus c. So that's your answer for number 11. For number 12, this looks like some sort of crazy like quotient rule sort of thing that we don't know how to do yet, except for this, we can use the love connection here. We can divide both of those in the numerator. So what we can do is we'll have the integral of x over the square root of x dx plus the integral of 5 over the square root of x dx. And so when we integrate, whenever we look at this, this simplifies here. This is x to the 1/2 power because you have an exponent of 1 in the numerator. That square root has an exponent of 1/2 in the denominator. You're going to subtract those to get x to the 1/2 power. And then here we will have 5x to the -1/2. power. And so we are going to integrate both of these. So we will have x to the 3/2 power. We have to divide out front by that 3/2, so we're going to have 1 over 3/2. Plus, now right now I'm not going to put a plus c with this part because I'm just going to put the plus c on the end after I've integrated everything. So here I've got x to negative 1/2. When I add 1 to negative 1/2, I'll get positive 1/2. And then I've got 5, and I've got to divide it by positive 1/2. And I will put a c here on the end. We don't want to leave these complex fractions, so dividing fractions is easy as pie. 1 times 2/3 would just give you 2/3 x to the 3/2. Plus 5 times 2 over 1 is just going to give you 10 x to the 1/2. And then we'll put a plus c there at the end. So this is our answer for that last example there. Your